Hi, in this video I'm going to show how to track people using a peopleACF detector and the Kalman filter and the MATLAB computer vision toolbox. The way that this is going to be done is that we're going to pick up a region of interest, which is the area that we are interested in not colliding with the persons when doing automated driving. And we use the ACF detector to detect the persons, and then create a track for each person that we find. And then in the next step, we keep using the ACF detector and detect new people, and then with that bounding box, if it intersects the expected bounding box from the predicted position using the Kalman filter, then we assign it to the track. And if we don't, then the track uses the Kalman filter until it loses confidence, and we delete the track and we keep creating new tracks. Okay, so let's start this example. The article is in the link of the description of this video. Let's hit open script, and that'll take us to here. And this function is this example is organized with nested functions. I don't like it because of the global variables, but that's how it is. Let's put a breakpoint, hit F5. First, we have the video that we're gonna use, and also we have a scale data file which basically has a map of well, we're gonna see that later. Let's set up the system object. First, we create the video reader to read the video, and the video player because we are gonna do some annotations to the images, and that's where we're gonna display our annotations in this video player. Okay, so let's load this pedestrian scale table, and that's basically a list that based on the height, which is the input, height of the relative to the image, we have a predicted bounding box height, and based on that, if it is too far away and according to a threshold, we can filter it out. Because, for example, let's say, okay, we have a bounding box that is like this, then we filter it out, or a bounding box that is this little. That's not possible, so we're gonna filter that out. Okay, so we create an ACF people detector using the caltech dataset. We initialize the tracks, and the tracks, this is a structure that we're gonna have for each track, which is the ID of the track, the color of the track. For example, in this we have green, one has green, the other one has pink, so that's the color assigned to the track. The bounding boxes for each track, the Kalman filter, each track, each one of these has its own Kalman filter, and the total visible count and age, these are taken into account when deleting the track. If it is not visible enough, for example, this person gets behind the car for too long, then we have to delete the track. And the confidence, which is also used in for deleting the track or displaying it, because although we can detect the person, we are only going to display it when it has enough confidence. But notice this example is very is not conservative enough. It doesn't have a false positives. It has a bunch of false. It has a bunch of false. It basically doesn't detect the object anytime, all the time, and that's in applications of this type. You want to detect. It's better to say, there's a person there when there is not, rather than saying than really having a person and not flagging it, because that could be dangerous. But anyway, that's how the example is done. Okay, so let's keep going. Okay, so we have some parameters. The region of interest, as mentioned before, is this red box in which we are interested in detecting the person. Okay, so we have the thresholds that we are going to use along the algorithm, and here's the core of the algorithm. So we have first we read the frame, detect the people using the peopleACF detector, then predict the new location of the bounding box using the Kalman filter, and then we use a couple of computer vision methods to classify if the new detection belongs to an existing track, or an existing track didn't have any detections, or detections that didn't have a corresponding track. And for each of these, we have these 4 methods. And for the unassigned detection, we have to create a new track. For the unassigned tracks, we have to update it using the Kalman filter and delete it if it is invisible or the confidence went too low. And they assign the new detections to existing tracks using this. Okay, so let's go and detect the person. First, we have a resize ratio. We detect it using the people detector. This is a method of the people detector, and this is the region of interest. Okay, so with that we have the bounding box of we have it empty, so this is a bad case. So let's put a breakpoint and get here when this is not empty. I'm gonna pause this. Okay, so let's change this condition. Set when it's not empty, keep going here. So I'm gonna keep going, and that keeps running the video, and this is going to be the first person. So we detect that person, and now we have a bounding box. So let's clear this breakpoint, and I'm going to resize it. I'm going to take the height, which is 35, and then take the minimum between the length of the table, and basically we want to access the table based on the height, which is the minimum y of the bounding box plus the height. So that will be 118, and we had to clamp it according to the size of the table, and we use the estimated height, which is 32, and get the difference. And if it is not above the threshold, then it is valid. So in this case, valid, so we don't lose the bounding box. And with that, we select the strongest. That's for the case we have multiple bounding boxes, but in this case we only have one, so we just only get the only one. And then we compute the centroid by having the minimum x added by the half of the height and half of the width, and with that we get the centroid, which is a two-dimensional point. Okay, so now we have the new detection. This doesn't apply yet because we don't have any track, and we're going to the detection. In here, basically this is going to be empty because this comes from the Kalman filter, the predicted box. So we are going to have an empty. So actually, yeah, what's going to happen here is that we have a cost of empty, and this is going to be ready saying, okay, you don't have any cost. This is the computer vision toolbox function that, given the cost, is going to give you the classification of the mapping between the tracks and the detection. This is a very common pattern to the point that MATLAB has a function for it. So the first, we don't have any assignments. This is empty because we don't have tracks. Let's just run it. Okay, this is empty because we don't have tracks. This is empty because we don't have tracks. So we have an unassigned detection, which is the only one that we have, is detection number 1. So we cannot run this method because there's no tracks, nothing of this, but we have a unassigned detection. So we have to create a new track for it. So let's go down in here. So yeah, let's go down in here. Okay, so the only track is number 1, so we're gonna get the corresponding centroid, bounding boxes, and scores for it. So we get this is for the case that there are more than one, but we only have one. So we create a Kalman filter with constant velocity and create a new structure for the track. It's the number 1, so we have the ID number 1, which is incremented for each track, and we have a random color for it, and the bounding box of the detection, the score, which is 21. Put the Kalman filter in here, set the visibility to 1, confidence is gonna be, this is gonna be the maximum confidence and the minimum, but at the beginning is the same score. And this is the collection of scores and the predicted box, which is the same box that we have. Okay, and then put the track into the list of tracks. So now we have at least one track. Okay, so let's keep running this. And now in the next loop, we're gonna have another detection, and let's see what's gonna happen in predict new locations. So here we have a track, so we're gonna use the Kalman filter. We use the previous bounding box, so we're gonna see how. We use the predict method from the Kalman filter, and that's gonna give us a centroid because the Kalman filter is based on centroids. And then use the previous bounding box to assign the width and height to that to the bounding box predicted by the Kalman filter. So we have a bounding box coming from the Kalman filter like this. Okay, and now with that bounding box, we can enter these detection assignment tracks. So now we can do an overlap. So we're gonna do an overlap between what the Kalman filter gave us and what the peopleACF detector gave us. And it's no surprise that the overlap is 1 because they're almost identical. So the cost is going to be 0. So what we want to do is that when the overlap between the Kalman and the ACF is completely, the more overlap, the more is closely related to the track that we already have. So we want for that we want to give a cost of 0, and we have a cost of 0. So if there's no overlap, then it is going to be 0, so the cost is going to be 1. And then if you are about 0.9 in here, the cost is going to be exacerbated and elevated to 100. So basically the thing is, if you don't overlap, then you don't assign that detection to the track. So okay, so let's keep going, and for that there's no surprise that we get the detection 1 is assigned to track number 1, and you don't have unassigned tracks because the track was assigned. So this is empty and this is empty. But let's take an interesting case, which is when the predicted boxes, the number of boxes is higher than 1, and the bounding boxes size, the number of bounding boxes is higher than 1, because in this case we're gonna have a matrix. So let's break when that happens in here. Okay, so now yeah, this is gonna, yeah, I should not have skipped that, but I'm gonna take it later. Okay, so now let's go to the display. The display, this one is gonna take the bounding boxes. I'm not gonna go much detail on this, but the thing is that it's gonna take the confidence and the age, and based on the confidence, if it is good enough, it's gonna be inserted using a field rectangle with opacity, and it's gonna insert the annotation using the peripheral and the confidence. It's gonna put it into annotation. So what you're gonna see in here is something like this with transparency and the confidence, but it has to have enough confidence to be inserted in there and be placed in the video. So I'm not gonna go in much detail about that. So let's go for the interesting case, the one that we have multiple bounding boxes. So yeah, it's running. It only have one detection. So yeah, that's basically the basic case that we went out. The track is gone at that point. Now we have a couple of bounding boxes. We have 2 tracks, so we have 2 predicted bounding boxes, and we have 2 detected bounding boxes. So let's see at the cost, what we have in the cost. So how can we interpret this? Okay, so we have to mix and match. So we have the first track doesn't intersect at all with the first detection. You can see that 357 plus 21 is well to the left of the 390. So this doesn't intersect, so you get a value of 0 in here. You get a value of 0 in the intersection, so the cost is going to be 1. So detection number 1 is not going to be assigned to the track number 1. But if you take a track number 1 and put it against detection number 2, you see that they do intersect. So basically the score is going to be close to 1, and the cost is going to be close to 0. So detection number 1 is going to be assigned to this one. But track number 2 doesn't intersect with number 1 for the same reason. So you get a score of 1, a cost of 1. And then there's a little intersection between the second track and the second detection, but it's very little, so the cost is higher than 91. Since all of these are above the 0.9 threshold, you're gonna get a high score for it in here. It's gonna be exacerbated. So you can see that track number 1 is gonna be assigned to detection number 2. Track number 2 is not gonna get any detection, and detection number 1 is gonna be unassigned. So when you pass this matrix, that's all this function takes. It's gonna do the proper classifications. So we have track number 1 assigned to detection number 2, track number 2 is not assigned, and detection number 1 is gonna be unassigned. So let's clear this breakpoint. And so now what's gonna happen? All these classifications are gonna go in here, and we are gonna say, okay, so track number 1 is gonna be assigned to detection number 2, and we are gonna get the bounding box, the centroid, the same as we did before, and we're gonna assign the centroid. We're gonna update the Kalman filter with the new centroid and improve the score and recompute the confidence based on the max and minimum. And for the unassigned track, we are gonna use again the Kalman filter, predicted position, and the score is going to be 0, so the confidence is going to be lower. And because of that lowered confidence, when we go to check for deleted tracks, we're going to see, okay, now we have 2 tracks, but that one went below the visibility, below the confidence threshold, so we're going to get rid of it. So we can see now that we have only 1 track. Okay, we lost that track because it didn't have good detection. Okay, now, but we have an assignment number 1 that didn't have a track. So for that one, we have to create a track for it. We create a new Kalman filter, a new track, and then eventually now we have a couple of tracks for the new detection. And then we keep displaying. So that's it. Let's run it till the end. So yeah, there's no people here. It's very conservative. I mean, yeah, there's one person. This should have, it has a lot of false negatives, and it is better to have false negatives than having false positives. No, the opposite around, my bad. Yeah, so that's it for the video. Thank you very much for watching.